The solar system has a tilt, not a small one, not a rounding error, 15 degrees. The plane that the outer planets should orbit in, the one you can derive from Newton's laws and a century of careful measurement, is warped. Something is pulling it out of alignment, and for a long time, nobody had a good answer for what. Here is why that matters. The invariable plane of the solar system, the true equator of the whole system, set by the combined angular momentum of every planet and every rock, should be flat. Not perfectly flat, but statistically flat, within a degree or two. The outer solar system's small frozen bodies, the ones beyond Neptune, should orbit close to that plane. Most of them do, but when astronomers map the full population and look at the disk they collectively define, it bends, 15 degrees off from where it should be. That is not noise, that is a signal that needs a cause. Gravitational anomalies in the outer solar system are not new. Astronomers have been arguing about orbital clustering in trans-Neptunian objects for over a decade, which is where the Planet 9 hypothesis came from. But this is something different. The warp in the invariable plane is a separate measurement, a separate line of evidence, and it points to a body in a specific place doing a specific thing to the geometry of the outer disk. A team at Princeton ran the numbers. What mass, at what distance, on what kind of orbit would produce exactly this tilt? The answer they came back with is striking. A rocky planet, somewhere between the mass of Mercury and the mass of Earth, orbiting the Sun between 80 and 200 astronomical units out. For reference, Neptune sits at 30 astronomical units. We are talking about a world 2 to 7 times farther from the Sun than the most distant planet we have ever directly observed, sitting out in the dark, never discovered, never photographed, never named. Until now, possibly, they are calling it Planet Y. This is not a confirmed discovery. Planet Y has not been seen through a telescope. It has been inferred, gravitationally, mathematically, from the shape of the outer solar system's geometry. The same way Neptune was inferred from irregularities in Uranus's orbit before anyone pointed a telescope at the right patch of sky. The inference preceded the observation by years. Nobody doubted the math. And when Johann Galle trained his telescope on the coordinates Leverrier had calculated, Neptune was there, within 1 degree of the predicted position. The question now is whether Planet Y is the same kind of story, a gravitational ghost waiting to be confirmed, or whether the signal resolves into something else entirely once we can actually look. And for the first time in a generation, we have an instrument capable of answering that question. To understand why that instrument matters, you first need to understand what it's looking for, and why finding it is so hard. Beyond Neptune, roughly 40 astronomical units from the Sun, the solar system doesn't just stop. It keeps going, in the form of a vast scattered population of small, icy, and rocky bodies called trans-Neptunian objects. Most people have heard of Pluto, which is one of them. But Pluto is just the nearest, brightest example of a population that numbers in the hundreds of thousands, possibly millions, spread across an enormous volume of space. These objects are slow, dim, and distant. They take centuries to orbit the Sun. The farthest known ones have orbital periods measured in thousands of years. But here's what makes them useful. Because they're so far out, and because they interact weakly with the inner solar system, their orbits preserve information. They're gravitational fossils. The shapes of their paths through space still carry the imprint of whatever tugged on them billions of years ago, or is tugging on them right now. Astronomers study this population by cataloging their orbits and looking for patterns, not the orbits of individual objects, but the statistical distribution of the whole population. The angles, the orientations, the tilts. A completely undisturbed outer solar system should produce orbits distributed randomly around what's called the invariable plane. The invariable plane is essentially the solar system's center of mass in angular momentum terms, a flat reference surface defined by the combined gravitational pull of all the planets. Jupiter dominates it, Saturn helps, everything else is a rounding error. The invariable plane is as flat and as well-defined a baseline as orbital mechanics can give you, and it should be where the solar system's overall motion lives. Now here's the anomaly. When researchers at Princeton analyzed a large sample of trans-Neptunian objects with well-characterized orbits, they found a collective tilt, a warp, in the expected distribution. Not random scatter, not a fluke in 1 or 2 objects, a systematic 15-degree deviation from the invariable plane running across a meaningful cross-section of the outer population. 15 degrees sounds modest until you run the statistics. The probability that this warp emerges by chance, from random orbital orientations with no underlying gravitational cause, is extremely low. The signal has the character of something physical, not something statistical. The outer solar system is leaning, and it's leaning in a direction that requires an explanation. The most economical explanation for a warp like this is a massive body orbiting in that general region, exerting a continuous, coherent gravitational influence on the surrounding population over long timescales. The shape of the warp constrains where the body is, roughly how massive it has to be, and what kind of orbit it's likely on. That's not speculation, it's the same gravitational inference that has located unseen bodies in the solar system before. The question is what mass and distance produce exactly this warp. That's where the Princeton team's math comes in. The Princeton team started with the warp itself, its angle, its coherence, the direction it points, and worked backward. Given this distortion, what body produces it? That's an inverse problem, and inverse problems in celestial mechanics have one saving grace. Gravity doesn't leave ambiguous fingerprints. The mathematics of orbital perturbation is well understood enough that you can constrain a perturber's mass and distance to a meaningful range, even without ever seeing the thing directly. So here's what the numbers actually say. The mass range the team landed on sits between roughly the mass of Mercury, about 5% of Earth, and the mass of Earth itself. That ceiling matters as much as the floor. An object more massive than Earth, sitting in the outer solar system, would produce a much stronger, broader disturbance. The warp would be steeper, its influence detectable across a wider arc of objects. That's not what the data shows. The signal is real but restrained, the gravitational footprint of something relatively modest by planetary standards. The orbital band the team infers is between 80 and 200 astronomical units from the Sun. For scale, Neptune sits at about 30 AU. 80 AU is more than twice as far out. At 200 AU, you're at a distance where sunlight takes over a day to arrive, where temperatures hover near absolute zero, and where a full orbit takes somewhere between 700 to 2,000 years. A body in that band would complete perhaps 1 or 2 laps around the Sun in the entire history of recorded astronomy, which is part of why nobody's spotted it. But here's the part that actually distinguishes this from prior outer solar system theories. The mass constraint rules out a gas giant. Not weakly, cleanly. A gas giant in this region, even a small one like Neptune, sits at 17 Earth masses minimum. Planet-wise, inferred maximum is 1 Earth mass. These aren't overlapping ranges. Whatever is producing this warp is dense and compact, not a diffuse envelope of hydrogen and helium. It's a rocky body, the same family as Mercury, Venus, Earth, and Mars, just stranded at a distance roughly 100 times farther out than any of them. The direction of the warp adds a further constraint. It doesn't point just anywhere in the sky. The tilt has a preferred plane, which the team used to narrow the search region significantly. Planet Y isn't inferred to be drifting through some arbitrary orbit. There's a zone of the sky, a slice of the ecliptic, where the math says it almost certainly lives. That localization is what makes this testable and not merely theoretical. What's striking is how spare the inference is. No images, no direct light, just the collective orbital behavior of a population of small, distant objects, and the logic that something coherent has been pushing on them. The confidence doesn't come from a single dramatic detection. It comes from gravitational bookkeeping. The solar system's ledger has an entry that doesn't balance without a body in that range, at that distance, in roughly that direction. Planet Y is the solution that closes the books. Whether it's the right solution is a different question, but the math gets you there. That closes the books on Planet Y. But here's where it gets complicated, because there's already another ghost on the ledger. For more than a decade, a different group of researchers has been building a case for a completely separate, undiscovered planet in the outer solar system. They call it Planet 9. And the moment you hear about Planet Y, the obvious question is, are these the same thing? Are two teams just finding the same body by different methods and giving it two names? They're not. The differences are specific, and they matter. Planet 9, as originally proposed by Konstantin Batygin and Mike Brown at Caltech, is a much larger body, estimated at roughly 5 to 10 Earth masses. That puts it in super-Earth, or mini-Neptune territory, not a rocky terrestrial world. Its proposed orbit is also far more distant, somewhere between 400 and 800 astronomical units from the Sun, possibly farther. Planet Y, by contrast, sits between 80 and 200 AU and carries a mass closer to Mercury or Earth. These aren't variations on a theme. The numbers don't overlap. The anomalies driving each inference are also distinct. Planet 9 was proposed to explain something different, a clustering of elongated orbits among a specific class of trans-Neptunian objects called extreme TNOs, whose perihelia, their closest approach points to the Sun, seemed to be herded together in a way that looked gravitationally shepherded. The argument was that a large, massive body on a wide eccentric orbit was acting like a sheepdog, keeping those orbits aligned. Planet Y's driving anomaly is the 15-degree warp in the invariable plane itself. A different population, a different measurement, a different geometry. The Princeton team wasn't looking at extreme orbital clustering. They were looking at the mean plane of the entire trans-Neptunian disk and finding it bent out of position. Two separate anomalies, measured in different populations, pointing to different distances, different masses, different orbital signatures. The most natural reading is that they are two separate bodies. That possibility, two undiscovered planets in our own solar system, both inferred from gravitational fingerprints we left unread for decades, is either deeply exciting or a sign that both inferences will eventually collapse under scrutiny. Science doesn't owe us a tidy answer. But the fact that the evidence streams don't contradict each other is worth noting. They're not competing explanations for the same data. They're independent claims about independent phenomena. Planet 9's status remains genuinely contested. Some statistical reanalyses have argued the clustering it was inferred from is weaker than it first appeared, possibly an artifact of observational bias. The simple fact that we've looked harder in some parts of the sky than others. Planet Y faces similar scrutiny. The warp signal is real in the data, but a signal in the data and a planet in the dark are not the same thing. The gap between those two statements is where the science actually lives. What neither inference has yet is a direct detection. No image, no spectrum, no confirmed orbit. Both bodies remain mathematical arguments. And that's exactly what makes the next question the one that counts. Where did Planet Y come from, and what would its presence in that orbit actually mean for how this solar system was built? So take the question seriously. If there is a rocky body somewhere between 80 and 200 astronomical units from the sun, how did it get there? Because nothing in our standard picture of planetary formation puts a terrestrial planet that far out. The inner solar system is where rock condenses close enough to the sun that silicates and metals could clump and collide and build something solid. The outer solar system is ice and gas. A Mercury to Earth mass rock sitting alone in the dark at 100 astronomical units is, by that picture, an anomaly that needs an explanation before it needs a name. Two explanations are on the table, and they point to completely different histories for the solar system. The first is capture. The early solar system was not the quiet, clockwork arrangement we inhabit now. For the first few 100 million years, it was chaotic. Planets migrating, gravitational resonances flipping, debris ejected in every direction. The outer disk was also embedded inside a stellar nursery, a dense cluster of young stars packed close enough that gravitational encounters between neighboring systems were not rare events. They happened. And when two stellar systems passed near each other, objects could be exchanged. A rogue body, a planet that formed around another star and was then flung loose, could have drifted into our sun's gravitational well during one of those close encounters and simply stayed, captured. The sun's gravity deep enough to trap it, but no inner planet ever strong enough to pull it inward. It would have settled into an eccentric, tilted orbit at exactly the kind of distance Planet Y's inferred position describes. There is observational support for the capture scenario in a broader sense. We know rogue planets exist, free-floating planetary mass objects, unbound to any star, drifting through interstellar space. Microlensing surveys suggest they may actually outnumber stars in the galaxy. The early solar system's stellar environment was dense enough that a capture event isn't a stretch. It's arguably expected. The question is whether the specific orbital signature of Planet Y is more consistent with a captured body than with something that formed here. The second scenario is in situ formation, not capture from outside, but a planet that built itself right where it sits, or close to it, out of the outer disk material that was present in the solar system's earliest phase. Models of protoplanetary disk evolution allow for rocky or mixed composition bodies to accumulate at large distances if the disk is massive enough and lives long enough. This planet, under that scenario, never migrated inward. It formed in the cold outer disk, grew to roughly its current mass, and then the disk dissipated around it, leaving it marooned. Gravitational interactions during the later chaotic phase could have pushed it into its current eccentric, tilted orbit without ever sending it all the way in. These two scenarios make subtly different predictions. A captured rogue body would likely have a more extreme orbital inclination and eccentricity than one that formed in the native disk. A foreign object tends to arrive on a tilted, stretched path that only partially circularizes over billions of years. An in-situ body should have an orbit that, however eccentric, still carries the rough memory of the original disk plane. Pinning down Planet Y's actual orbital parameters, its inclination, its eccentricity, the full shape of its path, is therefore not just a question of finding it. It's a question of reading its autobiography. What both scenarios agree on is this: neither is strange, both are physically plausible, both have precedent in what we know about solar system dynamics and planetary formation, which means the answer, whenever it comes, will not be exotic, but it will be decisive. One of two completely different histories for the outer solar system will be confirmed and the other ruled out. That kind of clarity is rare in planetary science. The instrument that delivers it is already running. That instrument is the Vera C. Rubin Observatory, sitting at 2,700 meters on Cerro Pachón in the Chilean Andes. And calling it an instrument almost undersells it. It's closer to a time machine pointed at the sky. Here's what makes it different from everything that came before. The telescope's primary mirror is 8.4 meters across, which is large, but not unprecedented. What's unprecedented is what's behind it. A camera with a 3.2 gigapixel sensor, the largest digital camera ever built for astronomy, capable of imaging a patch of sky roughly the size of 40 full moons in a single exposure. Every 3 or 4 nights, it photographs the entire visible southern sky. Then it does it again and again. For 10 years straight. That program has a name, the Legacy Survey of Space and Time, LSST. It isn't designed specifically to hunt Planet Y. It's designed to do essentially everything at once. Catalog billions of galaxies, track near-Earth asteroids, map the Milky Way's stellar population, catch supernovae as they happen. Planet Y is one thread in a survey fabric that covers all of observational astronomy simultaneously. But for the outer solar system, LSST is a revolution. The problem with finding trans-Neptunian objects historically has been cadence and depth. You need to see faint things repeatedly, across months and years, to build the orbital tracks that reveal how they're actually moving. Previous surveys could manage one or the other, deep imaging or wide coverage, rarely both at scale. Rubin does both, every few nights for a decade. What that means practically, within the first 3 to 4 years of full operation, LSST will have cataloged more trans-Neptunian objects than all previous surveys combined. The current sample, the one the Princeton team used to detect the warp, runs to a few hundred well-characterized orbits. Rubin will extend that to tens of thousands. The statistical signal that currently sits at the edge of significance will either sharpen into something undeniable or dissolve into noise as the real underlying distribution comes into focus. And if Planet Y exists at 80 to 200 astronomical units, with a mass somewhere between Mercury and Earth, Rubin has a real chance of imaging it directly. A rocky body at that distance, reflecting sunlight, sits right at the edge of what the telescope can detect. It won't be easy. It won't be obvious on the first pass. But as the survey accumulates years of sky coverage, a slowly moving point of reflected light at the right distance and brightness would accumulate exposures, and the pipeline that processes Rubin's images, designed from the start to catch exactly this kind of slow transient, would flag it. So the observatory doesn't just test the gravitational inference indirectly by adding more TNO orbits to the warp calculation. It has a plausible path to finding the object itself. Confirmation, or absence where something should be, which is its own kind of answer, and in some ways a harder one. Let's say Rubin finds it, a slow-moving point of light at 130 astronomical units, brightness consistent with a rocky body the size of Mars, orbit threading right through the band the Princeton team predicted. The pipeline flags it, a second instrument confirms it, Planet Y is real. What happens next isn't just a press release, it's a rewrite. The standard model of solar system formation, the one taught in every undergraduate astronomy course, the one embedded in every textbook printed in the last 30 years, says that rocky terrestrial planets form in the inner disk, close to the sun, where the chemistry and the collision rates are right. The outer solar system, past Neptune, is where you get ice giants and gas giants and Kuiper Belt debris, not rock. Not something Mercury to Earth in mass, sitting quietly at 130 AU, apparently having been there the whole time. A confirmed Planet Y breaks that picture at its foundation. Either the disk extended far enough and densely enough to build a rocky body at those distances, which would mean our models of how early solar disks dissipate are wrong in a fundamental way, or it arrived from somewhere else entirely, a captured rogue from the chaos of the early galaxy, which raises its own set of questions about how common such captures are and what other systems might harbor. Neither answer is comfortable. Both are extraordinary, and it doesn't stop at formation. Planetary architecture, how many planets a system has, where they sit, what sizes they reach, is one of the central questions in exoplanet science right now. We've cataloged thousands of planetary systems around other stars, and one of the most persistent puzzles is that they don't look like ours. Many of them have large rocky planets or super-Earths in orbits our own solar system seems to be missing. The current explanation is that our solar system is just shaped differently, that we went a different path. A confirmed Planet Y sitting in the deep outer system would suggest the path was stranger than we thought, and that the inventory we've been working from is incomplete. There's also the question of what else we've missed. If a Mars-to-Earth mass object at 80 to 200 AU went undetected until its gravitational fingerprint showed up in the tilt of the outer solar system, the natural follow-on is unsettling. What else is out there? The outer solar system is dark and vast, and we have barely begun to map it at the sensitivity level Rubin now makes possible. Planet Y, if confirmed, isn't just a discovery in itself. It's an argument that the census isn't finished. That's what makes the next decade genuinely consequential. Not just whether one candidate object exists, but what that answer tells us about every assumption we made when we thought we already knew the shape of our own solar system. And that assumption, that we had the basic inventory right, is the thread that keeps unraveling. Not once, not twice. The outer solar system has a habit of proving us wrong on a schedule we don't set. Pluto was supposed to be alone out there. Then we found the Kuiper Belt. The Kuiper Belt was supposed to be the edge. Then we found objects beyond it, clustering in ways that pointed to something massive we couldn't see. Now those clusters have a tilt, 15 degrees off a plane we thought was flat, and the math points to a body we have never detected, orbiting in a dark band between 80 and 200 AU, massive enough to bend the architecture of everything around it. Every time we looked harder, the solar system got stranger. That isn't a coincidence. It's a measurement problem finally meeting the instruments it deserved. What's different now is that Rubin doesn't just give us better eyes. It gives us a systematic answer, not a candidate here, a hint there, a decade-long survey that will either find Planet Y or place an upper bound tight enough to close the door. Science operating the way it's supposed to. A prediction, a test, a verdict. The 10-year wait is real. There's no shortcut. The sky is big. The object is small by planetary standards. The light it reflects is almost nothing against the dark. But patient systematic coverage is exactly what this kind of search requires. And for the first time, we have the machine to do it. What the Princeton team handed us isn't a planet. Not yet. It's a gravitational argument, a signal in the tilt of 1,000 distant orbits that says something is out there pulling. That argument now goes to the telescope for judgment. If Planet Y is real, it will be the most significant addition to the solar system in a generation. If it isn't, the signal still needs an explanation. And whatever that explanation turns out to be will matter just as much. Science doesn't lose either way. The census advances, the outer solar system is dark, and it is vast, and for most of human history, we had no way to read it at all. We are, by any honest measure, still early. A 15-degree warp in the invariable plane is the kind of clue that arrives once in a career. The kind that makes you realize the map you were using had a blank edge you didn't even know to label. A decade from now, that edge gets a name. Or it gets stranger. Either way, we'll finally know what's there.